Good morning. So yesterday we were into governing scale analysis of hydrodynamic equations, that is the continuity equation and the momentum equation, and this was the energy equation. What we did yesterday was, these were the equations for the two-dimensional laminar incompressible steady flow, and we took these equations and did the scale analysis. We did the scale analysis and got the scale of the delta by L, that is the hydrodynamic boundary layer thickness, was REL to the power of minus half. Delta by L was of the order of REL to the power of minus half, and CFX was the order of REL to the power of minus half for flow over a flat plate. Today what we will do is, we will take the energy equation, and try to get the boundary layer, thermal boundary layer thickness, and also the Nusselt number for two cases. First we will do with liquid metals, that is Prandtl numbers less than 1, and next we will do for Prandtl number greater than 1. So let's get started with scale analysis of energy equation. For flow over a flat plate, that is understood. Okay, we are continuing the yesterday's case, flat plate. Now Prandtl number, we are considering Prandtl number less than 1, that is, it is for liquid metals, that is mercury, sodium, gallium, galliumstan, so on and so forth. Nu less than alpha, that is momentum diffusivity is less than the thermal diffusivity, which implies that delta is very much less than delta T. In the very first class, Professor Arun has taught how the Prandtl number influences the delta and delta T. So I am not going to explain you that. If Prandtl number is very much less than 1, delta is very much less than delta T. So if I take a flat plate, and on which the flow is taking place with a velocity of u infinity and t infinity, and this is the temperature Ts, which is maintained constant. So you have delta, this is delta, and delta T is greater than delta, this is delta T. Now that means the velocity profile is having variation only over length L, only for delta, this delta. The rest of the velocity profile is u infinity. Okay. On the other hand, you have the temperature profile, this is your temperature profile, this is your T infinity, and this is the Ts, and this is my thermal boundary layer thickness delta T. One of the interesting things what you can see here is that because delta is very much less than delta T, as you can see that, as delta T is very much greater than delta, or delta is very much smaller than delta, within the thermal boundary layer thickness, one can assume that the velocity is equal to u infinity. Within the thermal boundary layer thickness, we can assume that u is equal to u infinity. So if you take the continuity equation, del u by del x plus del u by del x plus del v by del y equal to 0. So you have u infinity by L is of the order of v is v by delta, because delta is very small. So that much, to that extent only v will vary, only till here v will vary, beyond that there is no v. So v is u infinity delta by L. Now the energy equation is u del T by del x plus V del T by del Y is equal to alpha into del square T by del X squared plus del square T by del Y squared. Now, what is the scale of u? The scale of the u is u infinity, and the scale of delta t, the scale of del t is delta t, which is Ts minus T infinity. That is what is the scale. So, that is delta t divided by L comma V is u infinity delta by L into delta t by, now what is the scale of y in the energy equation? The scale of the y in the energy equation is delta t, because the temperature is varying in the energy equation over height of delta t. Okay. So, you have alpha into del t by del x squared is L squared comma alpha into delta t divided by y squared is delta t squared. As you can see that this term can be neglected because delta is very much smaller than delta t, and here out of these two, delta t by L squared is smaller than delta t by delta t squared. So, if you neglect these two, you get u infinity delta t by L is of the order of alpha delta t by delta t squared. So, this will get cancelled out with this. So, you get delta t squared is of the order of alpha by u infinity. Now, what you do is you multiply and divide by, multiply on both sides by L. So, you get delta t squared by L squared is of the order of alpha by nu into nu by u infinity L. I have just multiplied and divided by nu. This is nothing but 1 by Prandtl number into 1 by REL. So, delta t by L is of the order of REL to the power of minus half and PR to the power of minus half. This is what we get for boundary layer, thermal boundary layer thickness. So, now what is the Nusselt number? How do I get the Nusselt number? So, to get the Nusselt number, I need to calculate Nu is equal to HL by K. So, what is my H? What is my H? My H is equal to, my H is K minus Kf del T by del Y at Y equal to 0 into L divided by Kf. So, that is equal to K, this is of the order of Kf into delta T divided by delta T, thermal boundary layer thickness. This is the scale of delta T into L divided by Kf. Kf gets cancelled out. Now, sorry, I have made a mistake here, that is, this is H is minus Kf del T by del Y at Y equal to 0 divided by Ts minus T infinity. So, here I should have one Ts minus T infinity which I get. So, that is, you have del T. So, this del T gets cancelled out. So, Nusselt number is of the order of L by delta T. That is, we have found that delta T by L is of the order of REL to the power of minus half, PR to the power of minus half. So, Nusselt number will be of the order of REL to the power of half, PR to the power of half. That means, Nusselt number increases with the increase of Reynolds number, and it increases with the increase of Prandtl number, which is intuitive, which is correct. So, this is what we get on the basis of, this is what we get the scales for Prandtl number less than 1. So, now what we do is, let us take up Prandtl number greater than 1. Prandtl number greater than 1 means they are either oils or water. For water, for example, at room temperature, Prandtl number is 6. So, in this case, delta is very much greater than delta T because nu is greater than alpha. Okay. In that case, so what happens is that you have the velocity profile. So, you have the flow over a flat plate, you have delta t, and this is your delta. Okay. So, you have the velocity profile varying for larger lengths, that is, this is your velocity profile within the boundary layer, hydrodynamic boundary layer. I am assuming the velocity profile to be linearly varying because it is very small. So, it is a reasonably good assumption. So, and this thickness is delta. Remember, there is a flow u infinity, T infinity, and my temperature of the plate is Ts. Okay. Now, this is delta, but the thermal boundary layer thickness is very small. Thermal boundary layer thickness is very small. This is delta T, this is Ts, and this is T infinity. This is T infinity. Now, let us get started with the how do I get this velocity profile. So, the velocity profile has to be varying linearly, u equal to my plus c. At y equal to 0, u equal to 0 implies that c equal to 0. But when y is equal to delta t, when y is equal to delta, when y is delta, u is equal to u infinity. That implies that m is equal to u infinity by delta. M is u infinity by delta. Now, when y is equal to delta t, what will be the velocity profile? That is u equal to m is u infinity by delta and y is delta t. So, the scale of the u at y equal to delta t is u infinity delta t by delta. Now, if you take continuity equation, del u by del x plus del v by del y is equal to 0. Now, the scale of the u you just now got, the scale of the u is u infinity delta t by delta, and the scale of delta x, del x is L, comma, or it should be of the order of v divided by, here y is of the order of delta t, because I am interested in the variation of the velocity within the thermal boundary layer thickness, because thermal boundary layer thickness is very small. So, v is of the order of u infinity delta t by delta into delta t by L. So, let us keep this v like that. Let us keep the v like that. Now, let us take up the energy equation. Let us take up the energy equation. In this energy equation, I have u del t by del x plus v del t by del y is equal to alpha into del square t by del x squared plus del square t by del y squared. Del square t by del x squared and del square t by del y squared. So, the scale of the u, as we have found, it is u infinity delta t by delta, and this is scale of del t is delta t divided by scale of del x is L, comma, v scale is u infinity into delta t by delta into delta t by L into delta t by delta t. This is of the order of alpha delta t by L squared, comma, alpha delta t by delta t squared. Now, if you see, what happens here, delta t gets cancelled out. So, both the terms are same. So, the left hand side scale is u infinity delta t by delta into delta t by L. That is the left hand scale. Okay. This is of the order of alpha. Here comparing these two, the scale of delta t by L squared will be lower than delta t by delta t squared, because delta t is very much smaller than L. So, this can be neglected. So, I end up getting alpha delta t by delta t squared. So, here if you compare these two, delta t gets cancelled out. So, you get delta t cube divided by L is of the order of alpha by u infinity into delta. Now, if you divide this side by L squared, okay, so you put 1 L here and delta by L here, and you all in the next step delta t cube divided by L cube is of the order of divide and multiply by nu, that is nu by u infinity L into delta by L, okay, that is delta t cube by L cube is of the order of nu by u infinity L into nu by u infinity L divided into alpha by alpha. There is a mistake here, this is actually alpha by nu. So, this is you get alpha by nu into delta by L. So, here we had found delta by L is of the order of REL to the power of minus half in the last class. So, if we substitute all of this, you get delta t cube divided by L cube. This is of the order of, this is nothing but 1 nu by u infinity L is REL, and nu by alpha, that is alpha by nu is Prandtl number, and delta by L is REL to the power of minus half. So, I get delta t cube divided by L cube is of the order of REL to the power of minus 3 by 2 into PR to the power of minus 1. So, that is delta t by L is of the order of REL to the power of minus half and PR to the power of minus 1 by 3. That is what you get delta t by L. Now, again Nu is equal to HL by KF. This will be of the, this is equal to minus KF del T by del Y at Y equal to 0 into 1 by Ts minus T infinity, Ts minus T infinity into L. This is the definition of H divided by Kf. This is of the order of Kf gets cancelled out, delta T divided by delta T into 1 by delta T into L. So, this gets cancelled out. So, Nu is of the order of delta T by L to the power of minus 1. So, we have gotten delta T by L already. So, Nusselt number will be of the order of REL to the power of half PR to the power of 1 by 3. Okay. So, we have gotten now results for, now Prandtl number less than 1 and Prandtl number greater than 1. That is, we derived for less than 1, this is the scale for less than 1 and this is the scale for greater than 1. Now, the question is, if Prandtl number is equal to 1, which case I should take, whether I should take the result of delta very much less than Prandtl number less than 1 case I should take, or Prandtl number greater than 1 I should take. If you recall, Prandtl number very much less than 1 means delta is less than delta t and we assumed that u is equal to u infinity. But if Prandtl number is greater than 1 means delta is greater than delta t and we considered that u is linearly varying. But if Prandtl number is equal to 1 means actually delta is equal to delta t. So, that means physically I cannot assume if delta is equal to delta t, I cannot assume that within the thermal boundary layer thickness u is equal to u infinity, because velocity is varying within the thermal boundary layer thickness also, because in a flat plate delta is equal to delta t. That means both velocity are varying and the temperature is varying. Under those circumstances, the assumptions what we have made for Prandtl number less than 1 are not valid anymore. So, you will have to consider the case wherein which you can, where Prandtl number greater than 1 result is valid for Prandtl number equal to 1 also. So, this is valid not only for Prandtl number greater than 1, but this is also equal to greater than or equal to 1, and this is also equal to greater than or equal to 1. So, that is what you can get from, so we have addressed and gotten the boundary layer thicknesses for Prandtl number less than 1, greater than 1 and Prandtl number equal to 1 as well. So, now the question is, we got the scales here, but when you really solve, so you will get, as I said in the last class, delta by L is 4.92 REL to the power of minus half, and CFX is equal to 0.664 REL to the power of minus half. But if Prandtl number is less than 1, so delta T by L we got the constant 1.77 and Nusselt number is 0.565. If Prandtl number is greater than 1, here it scales to 3.01 and 0.332. Okay. So, the order of magnitude analysis gives us the delta, the order of magnitudes of the, or the powers or the exponents of the non-dimensional numbers, and which non-dimensional number is important will come out from that. Now, if you really just take an example, I have just put an example here, Reynolds number 1000, if you take and a length of the plate as 1 meter, delta will come out to be at a Reynolds number of 1000, which is laminar flow. By the way, for flow over a flat plate, it is 5 into 10 to the power of 5 is the critical Reynolds number. Okay. So, critical Reynolds number is 5 into 10 to the power of 5. So, delta is 4.92 mm, and delta T for Prandtl number less than 1 is, that is Prandtl number 0.1 if I take. So, you get that as 17.7. So, if you take this 17.7 and for Prandtl number greater than 1, it is, so you get delta T as 0.03. So, so for Prandtl number less than 1, delta is greater than, less than delta T, and for Prandtl number greater than 1, delta T is greater than, less than delta. So, this is just showing through numbers to give you the feel. So, length is in meters, but it is 1 meter, but the boundary layer thickness is hardly in mm. That is what is coming out from this exercise. Okay. So, now the next important issue is, what do we understand? So, if I do experiments with one fluid, let us say air, can I use the same results for water? Is it possible? Yes, it is possible using what is called as dimensional similarity. We have done this, that is why I am not writing it again. If you take this equation, these are the equations which we get for steady incompressible laminar fluid with constant properties. This is what we had done in the previous class, that is while doing scale analysis we have done this. So, if you take this equation and these are the boundary conditions which you take. Now, if you non-dimensionalize by putting x star equal to x by L, y star equal to y by L, u star equal to u by u infinity, v star equal to v by u infinity, p star equal to p by rho u infinity squared, t star equal to t minus ts by t infinity minus ts, you will get the the continuity equation as this, and in the momentum equation you get a non-dimensional number REL. We have done this earlier, that is why I am not repeating. So, you get non-dimensional number REL. On the other hand, when you do the non-dimensionalization of the energy equation, which all steps are there, we have done this already when we derived in the previous class, we get REL and PR. That means this. So these are the equations. Momentum equation, you will get REL, where REL is rho u infinity L by mu, and when you non-dimensionalize the energy equation, you get the REL and PR. Now the question is, can I use the one fluid result with the other fluid? Yes, I can use, provided I keep the non-dimensional numbers same. That means, so you can take that if you do non-dimensional numbers same. So if you take flow over a body, let us say you have taken flow over body, and this is, let us say, u infinity 1, this is with water, and now you have u infinity 2 which is with air. Okay. Now you know that these parameters for non-dimensionalizing are L, U infinity, T infinity, mu, Cp, K and rho. If you non-dimensionalize, you found that Cfx, the momentum equation, consists of Reynolds number only. That means Cfx will be dependent on only the Reynolds number. But when you non-dimensionalize energy equation, you got Re and Pr. That means Nusselt number is a function of RePr. From scale analysis also we found that. But can I use the results for water, what I have gotten for water, can I use the same for air? Yes, I can use, provided for Cf1, Cf of water to be equal to Cf of air, I should keep Re of water equal to Re of air. If I keep the Reynolds number same in both the cases, in water and air case, I am going to get same Cfx. Now for getting the Nusselt number of water to be equal to Nusselt number of air, what should I keep? I should keep not only Reynolds number same, but also Prandtl number. That is, if Prandtl number of the water or fluid 1 is equal to Prandtl number of fluid 2, in that case I can use, if I keep the Prandtl number same, then Nusselt number also can be kept. Nusselt number will also come out to be same. Okay. So, but of course for air and water the Prandtl numbers are slightly different, so you cannot directly use the water result or the Nusselt number results what you get for water as air. But the Nusselt H you cannot use, but you can use the Nusselt number results. So in the coming classes what we will do is we will solve a problem where we will show that here, for example, in this problem we have taken two cases, that is, we have taken air, this is air, hydrogen is flowing and here air is flowing. Now there is length is different in the hydrogen case, air is different, temperature of the plate is different, temperature of the plate here is different, pressures are different. Now what we do is, the properties if I take at the appropriate temperatures. Now if I check the Prandtl number, you can see that the Prandtl number of the air and the Prandtl number of the hydrogen are same. And so if you keep the Reynolds number and the Prandtl number same, then the Nusselt number also has to be same. So the Prandtl number of hydrogen is equal to Prandtl number of air, and similarity exists as I told earlier. If the Reynolds number of hydrogen case is equal to the Reynolds number of the air case, if you keep that same, so how do I keep that same? V air L air by nu air into V hydrogen L hydrogen divided by nu hydrogen. So if you do that, so you substitute for length, for hydrogen air case is 60 mm, hydrogen case is 40 mm, you substitute for nu new air and new hydrogen, you get V air. Now with this V air, so if you do the experiment at that V air, that is 15.89 at a heat flux per unit length of 50 watt per meter squared Kelvin, so temperature is 30 and T infinity, temperature of the surface is 30 and the fluid is 23 degrees Celsius. If you substitute, the Nusselt numbers have to be same. If Prandtl number is same and Reynolds number is same, then in that case Nusselt number has to be same. So you can compute the H of hydrogen by doing experiments with air, because you have kept the Reynolds number and the Prandtl number for air and the hydrogen same. That is how you could get the HH2. Only point is, I have just done the, just look at this, how the properties I have gotten carefully. I am not, for the want of time, I am not explaining how I have gotten this. I have gotten from the properties, but for nu is function of mu by rho, so that's why I have corrected for nu1 by nu2 as P1 by P2. So whatever I get for hydrogen, whatever I get for air, I have corrected for hydrogen based on pressure. So that's the only thing. But the takeaway is that if the Prandtl number of hydrogen and air is same, if the Reynolds number of hydrogen and air is same, the Nusselt number for hydrogen and air is same. You don't have to do the experiments with hydrogen, which is very expensive and difficult to do. You can do the experiments with air and infer the results for hydrogen from the results what you have gotten for air. That is the takeaway from this example. Thank you. So in the next class we will be going into external flows and internal flows, so much about the non-dimensionalization and the conservation of mass, momentum and energy. Thank you.